Let me set up my timer to make sure I don't overrun. So pleasure to be here today at Q2B. In this talk, I'm going to talk about enabling distributed quantum computing with trapped ions. And this is sort of a subset of New Quantum's general mission, which is to build a quantum networking layer to allow to scale out any type of matter-based qubit modality. So this is how it works. Oh, this one, sorry, the green one. A few words about New Quantum. So we're a spin-out from the University of Cambridge. We're a 60 people company with a lot of diversity, whichever direction you look at, whether it's the discipline, so the network stack is a complex hardware problem, and we require everyone to work from like quantum error correction theorists to electronics engineers to optics engineers, to other dimensions such as gender balance and nationalities. And I'm Claire Gall. I'm part of the management team, and our founder, Carmen, our CEO, couldn't come this week, unfortunately, because of a knee operation, but she's really well. And with me, I have Ed, who will also be giving a talk, more sort of commercial-oriented talk this Friday. And Ed has expertise in these HSM, so hardware security modules that Vladimir was talking about in the previous talk. And so what is this like quantum networking stack as we see it? So if we think of classical computing, a lot of the most demanding applications that we have access today, such as high-performance computing or AI accelerator, all happened thanks to a network stack, which is about 40% of the hardware of data centers today. And key elements of this stacks, for instance, are a network interface card, which allows to send wave packets between different CPUs, and you have some kind of network router to be able to route these packets where you want, and you have also some clever way of distributing computing tasks on this distributed architecture. And in quantum, our assertion is that things will be actually fairly analogous, in that if you want to be able to build a quantum computer in a similar way, the thing you need to worry about is first a qubit photon interface, so something that allows you to go from a matter qubit quantum state into a flying qubit, a single photon. You then need what we call the quantum networking unit to be able to route this photon and generate entanglement between QPUs as you require. And our assertion as well is that in this distributed architecture, it would be really valuable to have the quantum error correction lie above the network. And so this is what we call distributed quantum error correction. And at New Quantum, we work on all these three aspects of the stack. So first, in this talk, I'm going to motivate a bit distributed quantum error correction. So let's say you want to do distributed quantum computing. So the brute force way of doing it is to somehow, build, to build your processors, and then somehow to build non-local links between these processors and partition your algorithm between your processors. But if you do things in that way, one question that hardware people will typically ask you is, okay, this non-local link is going to be really noisy, so how are you going to get it to be as good as the local link? And the answer to that question is way too many. This is not how you would build distributed quantum architecture. That would lead to a fairly inefficient operation. Instead, the best way to use these non-local links between quantum processors, which are bound to be noisy, is to place the quantum error correction above the network. And in this talk, I will show you that these noisy non-local links will be all you need to scale, and you won't need to pay the overhead of distillation, for example. And in the second part of this talk, again, focusing on the ion modality, even though we work with other types of qubit, we'll tell you a little bit about how these non-local links, we're planning to reach performance metrics, which we think will be really valuable for scaling quantum computers. So why put error correction above the network? If you create entanglement with photons, you pay the initial cost of transduction from, a matter qubit into a photon. But then essentially you can create entanglement links at the speed of light. Whereas if you think about a monolithic architecture and you need to create these long distance links, you typically need some type of shuttling to create this long range connectivity, which will give rise to a massive overhead in time, and this overhead will increase as you scale the system. This is not the case of photonic links. But having these long distance links is really valuable because it gives you access to a whole range of quantum error correction codes, such as quantum LDPC, which are very efficient. So they're so-called high encoding rate, in that you have a high ratio of logical qubits compared to the expensive physical qubits. And so in this presentation, I'm going to talk about a code family, which is not quite quantum LDPC, but very analogous, which is called semi-hyperbolic flow K code. The advantage of this code family is that it only requires 2 qubit parity checks. So you guys all know the surface code, which requires a wait for syndrome measurements on 4 qubits. These flow K codes only require you to measure a syndrome involving 2 qubits. So they're really hardware friendly. And so if you look at the performance of this code, so here I will look at a code whose little name is H144-F3. But what does it mean? What it means is, like, in this code, I'm creating 20 logical qubits using 3,000 data qubits. And the way in our model that we've sort of modeled this QEC code is by using 90 processors with 32 qubits in each processor. So that's pretty much a QPU size that quantum computing companies know how to build today out of trapped ions. And in this graph here, I'm showing you, as a function of the non-local error rate and the local error rate, where do I have in blue logical information that decays slower than the physical qubit. So you have error suppression in this region. And in the red, that's the region where you don't want to be in. You don't have error suppression. And what you kind of see from our circuit noise model is that for this type of code families, if you have local error rates, which on the order of a few 10 to the minus 4, which again is compatible with what the hardware delivers today, these codes are resilient to non-local error rates on the order of a few %. And that's where state of the art is. So it's a really like feasible way to scale quantum computers to fault tolerance, we feel. So we've published this work in a paper here, available on the archive. And we have loads of other interesting results. One of them has been sort of studying the sort of scaling of error suppression as you increase the size of the code. And we've done this for a local error rate of 99.97%, which is, realistic, and non-local fidelities on the order of 99%. And what you see is that lambda, this error suppression coefficient, is 5, which again is a really, really promising number if we're going to build this hardware. And what does that mean at the hardware level? So I really want to emphasize that the hardware underpinning these types of distributed quantum error correction is fundamentally modular. You only need one QPU to connect to roughly 10 other QPUs, which means that at the hardware level, what you can do is for any QPU, you can put a sort of switch matrix here with on the order of 10 outputs. And then by connecting one output from this QPU to another output and carrying a standard entanglement swapping via a bunch of beam splitters and detectors, you can really create the connectivity that is required for these codes. And then by stamping and repeating this sort of elementary module with a QPU, a qubit photon interface, and the switch matrix, you can sort of scale to bigger system sizes and suppress errors and get more logical qubits all at once. So New Quantum as a company, we're developing this whole hardware stack. But in the presentation today, I will now mainly focus on this qubit photon interface, which is really a bottleneck today to reach the entanglement rates that we need to scale quantum computers. So how do we build such an efficient photon extraction? Our approach at New Quantum is to use Fabry-Perot cavity mirrors. And you see here an SEM picture of such a mirror, which is about 100 microns in diameter. And in the picture below, you kind of see the size of the pins on which, at the top we sort of fabricate these mirrors relative to your finger. So these are really, really tiny mirror substrates. And so what do these cavities allow us to do? Well, nowadays, quantum networking, it's still a very active field of research. I've put down, the latest 2 academic results from Chris Monroe and David Lucas in Oxford. And right now, the state of the art is 97%, and it's 250 hertz entanglement rate. So, 250 entanglement clicks every second. And those rates, they're obtained with free space approach. So just putting a big lens to collect photons from the ion. What distributed quantum error correction will need, and again, that's specific to the ion modality, but it will be similar numbers for, let's say, neutral atoms, is so really this fidelity on the order of 99% would be really nice to have, but also the entanglement rate needs to be roughly 100 times faster. And so what do we get with our cavities? Oops. Sorry, there seems to have been a conversion error between Google Slides and PowerPoints. Oops, sorry. So here I'm kind of showing a plot of the finesse of our cavity mirrors when we increase the distance between the mirrors. And what this plot is kind of showing is that you can stay at really, really high finesse and really low unwanted losses despite increasing your cavity length. And you can work with a Fabry-Perot cavity, which is so-called concave-concave, which is really nice for trapped ions who likes the mirror surfaces to be away as far as possible. And what this means for us is that our cavities have low unwanted loss. We're typically at 100 ppm all in all. We have also a small cavity waste because we have this concave-concave cavities, so they're typically 5 microns. We are also optimizing the system for throughput, so we're aiming for 100 nanosecond photon time bins. And overall, the key number that is missing here is the end-to-end collection efficiency that we know we'll get if we are able to place this ion at the center of the optical mode of our cavity. And this will be 30%, and this will be an infrared photon. And that's going to be really powerful because that gives us 100x improvement over state of the art. The next thing you have to worry about is not only like making these cavity mirrors, but integrating them into an ion trap. And so for this, New Quantum has developed a trapped ion system, which is specifically tailored to integrate the cavity and to allow to overlap the ion with our cavity mode. This is done with high precision mechanical assembly in this generation. And in this picture here, you have a trap electrode and you have our cavity mirror, and we achieve exquisite precision when we passively assemble these systems. And by the way, all this electrode manufacturing was done in Japan. So the next thing you care about for building the quantum photon interface is picking the right type of ion. And there's this nice paper here from the Chris Monroe group where they've sort of drawn a list of all the ions that and atoms that you could think of using. So there's also neutral rubidium and strontium and so on. And they've been calculating the sort of entanglement error that you get from photon recoil. And what you can draw from this table is that fidelity will improve if you pick a heavy atom or a heavy ion. It will improve if you pick a red transition as opposed to a blue transition. And it will improve if the photon is short, because you'll accumulate sort of less phase uncertainty on your photon. And so in all, it turns out that strontium, as you can see, is kind of your best pick. And unsurprisingly, at New Quantum, we have picked strontium for similar engineering reasons. The only difference is in our case, I remind you, is that with a cavity, you tend to extend the sort of time, the photon length, the wave packet. And so you end up with a 100 nanosecond photon instead of this 8 nanosecond photon limited by the lifetime. And so with the ion trap systems that I've shown you in the previous slide, we're baking this system and we're hoping to demonstrate in the next 2 years a 2-node entanglement with 98% fidelity and greater than 10 kilohertz entanglement rate. With that, I'm perfectly on time. It's time for me to conclude. So what have I told you about today? I've spoken about how, thanks to the long-range connectivity and the quantum network layer, we could access efficient distributed quantum error correction I've also told you about these low-loss micro mirrors that New Quantum is fabricating, and about an ion trap proof of concept to demonstrate commercially valuable network link. And with this, I will thank you for your attention. I will thank also all the founders who found this work, and just mention that we're hiring as well. Thank you very much.